Hi everyone, I'll be lecturing on chapter 6, which is the structural analysis. My lecture covers 6.1, which is simple truss from textbook page 273, and the methods of join from the textbook page 276. So today's objective would be to define a simple truss and to determine the force members in the simple truss. So the reading quiz you may just answer by yourself. Now the application of a truss. So if you can see, this diagram here is commonly used in roof structures. So in roof structures there are two types. One is exposed and one is non-exposed. So what you have above your ceiling in your house is the non-exposed type, where it may not be as neat and aesthetically beautiful like what we can see here. Can you see the structure here? It's very neat and it's very beautiful. It's symmetrical, because why? This is a exposed roof truss. So for a given truss geometry and load, how can you determine the force in the truss members and thus be able to select their sizes? That is the main primary objective of learning this chapter itself. And the more challenging question is that for a given load, how can we design the truss geometry to minimize the cost? Remember what I always tell you, as an engineer, we always optimize our cost. So truss is also used for this kind of structure, where this looks like more like a go down, a place where to store your goods, temporary one. So for costing wise, we don't need to put a false ceiling in this place here. You just can just expose the truss itself. And then there are also applications like in a crane. Here you can see this kind of crane in construction place or some ports. And also you can see this structure probably in a factory, as they may have a conveyor belt up here, but in this case it's not a conveyor belt, it's just a platform. So if you can see, can you see here, this is also a truss from the basic triangle. Okay, so a simple truss. A truss is a structure composed of slender members joined together at their end points. So they are joined together at their end points. So a purlin, like in your roof, a purlin is a beam that runs across from this cross-sectional triangle to the other cross-sectional triangle. So you may have few more cross-sectional triangles in the middle, so the purlin joins them all together. So if a truss along the imposed load lies in a single plane, so we look at a single plane, which is known as the planar truss. A simple truss is a planar truss which begins with a triangular element. The basic one is triangle. There's a join here, there's a join here, and there's a join here, and can be explained by adding two members at a join. So for this truss, the number of joins, which is m, okay, and the number of members, which is m, and the number of joins, j, are related to the equation below here. So you have the number of members depending on the number of joins minus with 3. So the analysis and assumption, we have to take some design assumption in order to simplify the calculation in our textbook. So the first assumption would be all loads that's applied to the joints, the weight of the truss members can be neglected. So what does it mean by that? So let's look at what does it mean by that. One second, I'm trying to move the screen to that particular part. Okay, let's say you have a truss triangle like this. So this member has a weight, right? Definitely it has a weight, isn't it? And this filler also has a weight, and this filler has a weight. But in this case, for your statics class, we are going to ignore the weight here, ignore the weight here, and ignore the weight here. We're only going to emphasize on the joints. That's what the first assumption means. Whereas the second one, the members are joined together by smooth pin. So this member here is actually a smooth pin. A smooth pin. And assumption is satisfied in most practical cases where the joints are formed by bolting at the end together. Most time it's bolted together. And with these two assumptions, the members act as the force member, as two force member. So they are loaded in either tension or compression. Now, what does it mean by tension or compression? Now, let's look at this. Yeah, if a member, a rod, is on tension, then it will look like this. It pulls, is stretched. This is on tension. Okay. Whereas if it's on compression, then it is being compressed this way, squeezed in. Yeah, compression. Now, let me just specify another thing. If I were to redraw this tension here, if I have a member which is under tension, and if I cut in the middle, I cut in the middle like this and expose it. So what's going to happen? It's going to be something like this. One piece here in the middle cut, and another piece in the middle cut, another piece here. So this is also under tension. That's how it will be. Because to counter effect the force, this member will be something like this. So if you join together the middle part, it just disappears, something like this. Okay? Okay, next. So the method of joints. When using the method of joints to solve the forces in truss, the equilibrium of the joint beam is considered. All forces acting on the joint are shown in the free body diagram. So this includes all external forces as well as the forces acting in the member. Equations of equilibrium, Fx equals 0 and Fy equals 0, are used to solve the unknown forces. So which is the external force and which is the internal force? Okay, so this would be the free body diagram for joint B. So if you look at this diagram here, you have your 500 here, right? So this would be the labeled as external force. Whereas the other friend, the other members here and here, which is drawn here and here, are known as internal forces. Internal forces. So internal forces will have either compression or tension, whereas external forces will not be labeled as compression or tension. Yeah. Okay. So step for analysis. The first thing that you should do is, if the truss support reaction are not given, you have to draw a free body diagram. That's the most important, of the entire truss. But remember, do not draw a big structure. You have to go point to point. Next, this would be for the bigger structure. Next, you draw a free body diagram at the joint itself. At the joint itself, just one joint by joint. You have to draw joint by joint. Like, okay, example. Look at this structure, this whole thing. So first thing you draw is the whole free body diagram. Yeah, that's step 1. Step 2 would be joint by joint. Yeah, first joint B, then joint C, then joint A. That's how you do it. Yeah. Okay. Now next would be apply the scalar equation, which is the Fx equals to 0 and Fy equals to 0 to determine the unknowns. If the answer is positive, then the assumption of the direction tension is correct. So I'm going to show this in the next working. So repeat step 2 and 3 in each the joint for your succession. So before we go into zero force member, which is the next video, I will just explain to you what's going on. Okay, let's look at this structure. So the first thing to do is the step 1, like what I've explained just now, is to draw the whole structure like this. Okay, so we have what? External force AX and AY. Yeah. AY, AX, and then we have our C here. So C is in the direction of CY, and then we have our 500 here, right? So this is the first step. Now second step, what is the second step? Second step is you have to take from the joint. So you have to go for the least complicated joint. Like this fella has got 4 force member, 1, 2 internal, 1, 2 internal, and 1 external. This has got 1, 2 and 1 external and 1 external. 4 here, 3 here, and 1, 2. The third one we know, 3. So how many unknowns here? This is 2 unknowns, this is 4 unknowns, and this is 3 unknowns. So where would you go? You always go to the simple unknown, the least unknown. Yeah, so it would be joint B. So how to draw joint B? Okay, first you draw the point, next you draw the 500, then this one and this one. So this 500, no issue, you know the direction, you know the magnitude, no worries. But this 2, you don't know the direction, right? Okay, now remember the previous lesson, it says that your Fx, summation of Fx has to be 0. Also, your Fy have to be 0, right? Okay, so in that case, if you want to satisfy Fx equals to 0, so you need to have one pointing 500. If let's say in this case 500 pointing to the right, and definitely you have to have a counterbalance of 500 to the left, right? Correct or not? Yeah, so in that case, of course, this will not affect the 500. Yeah, it will not affect because this is perpendicular 90 degrees. So the only thing that will affect is this line here, the what do you call this, angled line here. So we have 45 degrees here. So what do? We have to balance this. So definitely this arrow has to be pointing upward, because if we put it in x-axis, it's going to be like 1 500 there and 1 500 this side. Yeah, so that would be the final direction. So I'm going to erase this and draw a nice one here, yeah, so that you don't get confused. So the original one was something like this and like this, right? So now we know the direction of this fella that's pointing this way. Okay, that's settled. So pressing in, it means it is compression. Yeah, okay, leave that alone. Okay, now let's look at this fella. Fy equals to 0. So if you have something which is pointing something like that, when you resolve it, it will be vertical upward, right? So definitely this partner will be pointing downward. So you have to name them. So don't just simply give any names that you like. So this would be from point B, right? From point B. So this would be BC and this would be BA. Sorry, I can't write. Oh, this is BA. BA. Okay, can? No problem. Okay, now we will repeat this for joint A. Okay, let's go to, no, I'm not going to go to joint A. I'm going to go to joint C first. Yeah, because joint C is this unknown again. Okay, so we have one flare here, one flare here, and one flare here, and one external force, which is CY. Okay, this is joint C. Okay, joint C. So, and then we have this force member which is called BC, or in this case it will be CB, and this fellow will be CA. So how did you get the name of CA and CB? Because joint C moving towards B, joint A moving towards A. So you just follow the name. Yeah. So from the previous one, you know your BC and CB is the same. So this is compression. So this fellow will also be under compression. So it's pressing downwards. Oh, this one you didn't know the direction, right? Sorry, you didn't know the direction. You have to guess the direction. Yeah, I went and draw the direction just now. It's wrong. Okay, it's just a straight line. We don't know the direction, but we know CB. So once we know CB, you will know CY, because you have to balance off Fx equals to 0 and Fy equals to 0. So that's the reason why CY is pointing that way. So now what about CA? What about our CA? Because CB is pointing here, so this will be actually pointing outward. Yeah. Okay, now let's repeat the whole thing for joint A. We have some hints here now. So joint A has got 4 that you don't know. Okay. Okay, from there, this is your AY, this is your AX, external. Yeah. And this would be AC, and this would be AB, right? So AB and BA is the same. So where is BA pointing? BA is pointing at tension, this away. So this will also be away. Okay. And where is AC pointing? So AC, where is AC from our previous calculation? Okay, AC is here. So AC is pointing away as well. So this will also point away. So with that, can you fill up the blanks of the others? Yeah, because it's pointing here, this will be pointing here, pointing up, so this will be pointing down. So this is like a jigsaw puzzle. You can solve one. You use this data to solve joint C, and from this joint C data you use to solve joint A. So that is how you solve this. Okay, let's just this is how to draw the free body diagram. Now let's solve a question. So this is from your textbook, example 6.1. So I want you to observe this carefully. Yeah, observe this carefully. So because I'm going to make you submit some work later. Yeah, okay, 6.1. Let's look at 6.1. Sorry, my stylus can't write on the PDF, so you just have to follow the mouse here. Yeah, okay, joint B. That's what you're drawn. Can you see? FBC, FBA, and then we have 500 here. 500 is existing. Yeah, so now you know how to put in the arrows pointing upward and downward, so that's settled. So let's solve joint B. From fx equal to 0, 500 existing in the question, minus FBC sine 45, because this one you resolve it to x-axis. So you get FBC 700.1. C. What is the C? C is compression. Look at the direction of FBC. It's actually pressing in point B. Okay. Now why is it like pressing on point B? Let's look at the drawing here again. Yeah. Okay. Now, let's just enlarge point B. So we have one force here, which is BC. So BC is connected by the rod, right? So you have another force here, which is CB, because it's on point C. It's point C, point B. So if you were to draw a free body diagram, a detailed one, yeah, this is the rod. Okay, this is at point BC, and this is at point CB. So if you join them all together, you can't see the force. That's the reason why this is known as internal force. Internal force. So in this case, this rod is actually undergoing, to just balance this, yeah, it's undergoing compression. Yeah, it's undergoing compression. Because this rod here, you see, if one flow go up, this flow must come down. Then only you cancel off, right? Okay, so this flow is going up, this flow is going down. So you can cancel off. That's the meaning. Yeah. So the rod is under compression. So that compression has actually caused compression on the joint as well. So that is the meaning of this. So let's look at this. Yes, it's correct. It's compression. Yeah, it's compression. Next line. FBC cos 45 minus FBA equals to 0. How is that done? This is Fy equals to 0. So we have FBA pointing downward minus with FB cos 45 resolved from this pointing upward. So it will be 500 tension. Okay. So that's done. Next, proceed to point C. So if we go to point C, can you see point C there? We have FCA. We have CY, and we have 707. Where did the 707 come from? From the previous up here. Yeah. So 707 is from up there. So here we have Fx equals 0, negative FCA plus 707.45. Okay. We have 500 tension. And then the same thing with Fy. Now repeat the whole thing with joint A. So this 500, this 500 comes from the previous working from joint C and joint joint B. So now we can solve for AX and AY. So watch out, AX and AY, you don't write it as tension or compression. It's just left it just like that. Yeah. So at the end of the day, look at this diagram. If you draw by the point, so you get that. If you draw the rod in middle, so this is how the tension is. See, tension there, tension on the point. If you mix up everything together, you cannot see anything except for the external force, which is what? Your AX, AY, 500, 500, and this 500, and also this 500. Yeah? Okay. So I hope you can understand what I've actually lectured to you. So your homework is to redo example 6.2 and example 6.3 in a piece of paper, and upload it on the link that I've actually posted in the e-learn itself. Yeah. So my next video will actually continue to zero force member. Yeah. Okay. Thank you.